gas loss. There are four basic properties of gases that we measure. You could say there's four variables. One is pressure, and we use capital P for that. Volume is important, we use capital V. The temperature is capital T. And the amount of gas, we're going to measure in moles, not in grams, and that's a lowercase n. Don't ask me why. You might think, well, that should be a lowercase m. I think the m's have been so used that they went with n instead. I don't know. But these properties are interrelated. If you change one, something else is going to change. And so the gas laws describe this relationship. Remember, a law says what happens, doesn't explain why. So Robert Boyle and Robert Hooke, who often doesn't get much credit for this, this is back in the 1600s, so a long time ago. The cool thing, though, about gases is they could do so many really neat experiments, even though they had like zero technology, right? They didn't even know what electricity was. So they used a J-shaped tube, and they looked at the relationship between the volume of a gas and its pressure. So they've got some gas in this end of the tube, and it's closed off. And they can look at the volume of it. If you know the inside diameter of the tube, you could measure the height of it, and you could calculate the volume of the gas, right? And then they can change the pressure by adding more mercury. So you add more mercury, and the difference in these columns, this height changes. You have more pressure inside than you did before. And look, the volume gets smaller. And so they looked at these and they made a lot of measurements. Okay, let's see what the volume is with this pressure. Let's make it bigger and see what happens and write down all these numbers. And what they observed was an inverse relationship. When the pressure goes up, the volume goes down. If you graph volume versus pressure, you get a curve like this. As the pressure increases, the volume decreases. And this relationship is called Boyle's law, in honor of the guy who did these experiments. So Boyle's law tells us that the volume is inversely proportional. It's proportional to 1 over the pressure. Now, in these experiments, it was important that the temperature remain the same and the number of moles of gas, the quantity of gas, remain the same. Because you can only look at so many things at once. You don't want everything changing all at once. So we see that graph of pressure versus volume is curved, but if we graph pressure versus 1 over the volume, we get a straight line. Oh, shoot, there should be one. We should have that graph in here, and it's not in here. I'm sorry. Anytime a scientist can graph data or some function of a data and get a straight line, we get really excited. Because then you can figure out a mathematical equation describing those. So what we come up with here, this is what we usually call Boyle's law. P1V1 equals P2V2. The pressure of the gas times its volume is going to be a constant if you've got the temperature and the amount of gas. So constant. And so if you change one of these, then the other will change in the opposite way so that still remains a constant. So the pressure of a gas times its volume under one set of conditions will equal the pressure times the volume under another set of conditions. And so we can use this and do all kinds of fun calculations. Here's another illustration. Here we've got a volume here of 1 liter, and the pressure is 1 atmosphere. If we double the pressure, so we're applying pressure here by putting a weight, a 1 kilogram weight or a 2 kilogram weight. If we double the pressure, the volume is cut in half. Volume times pressure here equals 1. Pressure and volume equals 1. Boyle's law relates to scuba diving. for every 10 meters of depth that a diver goes down, you're going to experience about 1 additional atmosphere of pressure. Doubling the pressure is pretty significant. So at 20 meters of depth, you go down 10 meters, you add 1. You go down another 10 meters, you add 2. So now you've got 3 atmospheres of pressure on you. That's significant, and you got to take that into account when you think about breathing. So if you go down 20 meters and you're experiencing 3 atmospheres of pressure, and you take a breath and you hold your breath and you ascend rapidly to the surface where the pressure is 1 atmosphere, what's going to happen to the volume of air in your lungs? It's going to expand a lot, right? Is that going to be good for you?
Oh, yeah.
Only if you like your lungs to explode. Because the pressure decreases by a factor of 3, the volume will increase by a factor of 3. Your lungs are not designed to do that. You will cause damage to your internal organs. So if you're a scuba diver, there's a reason they make scuba divers go to these classes and pass tests and stuff. Because there's some things that you just really need to know, or you're going to hurt yourself or kill yourself, right? Always exhale when rising from a dive. Okay, so let's look at an example here. Boyle's apprentice finds that the air trapped in a J tube occupies 24.8 cubic centimeters at 1.12 atmospheres. By adding mercury to the tube, he increases the pressure on the trapped air to 2.65 atmospheres. Assuming constant temperature, what's the new volume of air in liters? Okay, so we're gonna encounter a whole new group of word problems here. And we need to be able to pull the numbers out successfully. So we recognize this is involving gases. I highly recommend making a table. We're going to have 1s and 2s and P's and V's, and it's easy to get them confused, and a table is the simplest way to organize them. So we're going to have a condition 1 and a condition 2. We're just going to go through the problem and deal with the numbers as we come to them. First number, 24.8. So I'm going to write that down. 24.8 cubic centimeters. And then we need to know, what quantity is that? Pressure, volume, temperature, number of moles. That's a volume. We can recognize that from the units. It occupies that at 1.12 atmospheres, and that's a pressure because that's a pressure unit. So those two numbers were together in the word problem, right? That's one set of conditions. We don't care which one's first and which one's second. It really doesn't matter. We just need to get them paired up correctly. So that's one thing, and then it says he adds mercury. So now we're doing something. Things are changing. This is going to be condition 2. Now we get 2.64 atmospheres. So I'm going to write that in the pressure column. 2.64 atmospheres. Always include your units. They will be the death of you otherwise. Not literally. There we have a little table. And then the question is, what's the new volume? Well, let's call this V2. That is what we're trying to find. Now, it does say in liters. We're going to worry about that at the end. So we've got pressure and volume. We're going to use Boyle's law. P1 V1 equals P2 V2. We need to rearrange this equation and solve it so that we get V2 equals and all the other variables on the other side. Again, rearrange the equation first, then plug numbers in. So we want V2 by itself. We're going to divide this side by P2 so that we can make P2 go to the other side. So V2 equals P1 V1 over P2. if you have any dyslexic issues or tracking issues, be really careful, because it's so easy to mix up the ones and the twos. Okay, so just double check and make sure that you've got your ones and twos in the right places. This is not the only way to solve these problems. There's also a ratio method. Most students don't like that. And if you're a person who can think that way, you are also very capable of reading about it and doing it yourself. And so if you want to solve these by ratios, you go right ahead. It's a very good way, but it doesn't make sense to a lot of people. So we're going to use the more algebra method. So we rearrange the equation. Now we're going to plug in the numbers from the table where they're all nicely labeled. Pressure 1 is 1.12 atmospheres. Write the units. Volume 24.8 cubic centimeters. And pressure 2, 2.64 atmospheres. Now we look at the units and we see atmospheres cancel out. Cubic centimeter is a unit of volume, and so we're okay. Before we calculate the answer, let's try to predict, is the volume going to be larger or smaller? It'll be smaller. We can think about balloons when we think about gases. So if you think about a balloon and you think about putting pressure on it from the outside, is that going to make it bigger or smaller? Smaller. So we're going to expect the volume to go down. If it doesn't, then we know we did something wrong. So we got 1.12 times 24.8 divided by 2.64, and we get 10.5. So we get volume 2 equals 10.5 cubic centimeters. Okay? Is that the answer?
No.
No, it asks for it in liters. We need to convert. A cubic centimeter is exactly the same as a milliliter. And it's 10 to the minus third liters in 1 milliliter. So we end up with 0.0105 liters. Questions? In 1A, we do mess with your brain when it comes to units. You like to just throw units in there so you have to convert stuff. Another guy, Charles. J.A.C. Charles. So that now we're into the 1700s. Okay, so lived into the 1800s. He looked at the relationship between gas volume and temperature. And he found that the volume of a gas is directly proportional to its absolute temperature. If you think about a balloon, when you get a balloon cold, does it get bigger or smaller? It gets smaller. And if you warm it up, it gets bigger, right? You could try that at home if you want. Take a balloon and kind of blow it up middling and put it in boiling water and watch it grow, and put it in ice water and watch it shrink. It's fun. So Charles' law, the volume is proportional to the temperature. Now this is the absolute temperature. We talked about the Kelvin scale, right? In gas laws, we always have to use the Kelvin temperature scale. The pressure and volume units, as long as they agree with each other, doesn't matter. If you want to use atmospheres or millimeters of mercury or pascals, it's fine in these simple gas laws. The temperature matters. The reason the temperature matters is because the conversion, the relationship is one of adding. Right, so, good grief. Kelvin equals degrees Celsius plus 273. That doesn't cancel out in these fractions. Okay, so this is This is super, super important. And this gas law work is actually where the idea of absolute zero and that temperature of minus 273.15 degrees Celsius came about. If you graph the volume versus temperature for different amounts of gas, we get these nice straight lines. So here is 1 mole of gas, and here's half a mole of gas, and here's a quarter mole of gas. You could do all different amounts of gas. The lines will have different slopes. They will all intersect at this one point. And it's minus 273.15 degrees Celsius. And that's called absolute zero. Because if you went any farther, you would end up with a negative volume. This is where the volume is zero. Can you get negative volume? No. Zero is zero. No volume is no volume. And so that's called the absolute zero. And we use that Kelvin scale because on the Kelvin scale, the intercept of all these lines is zero. Do you remember the equation for a line? Y equals what? Mx plus b. Okay, if we use the Kelvin scale, the b is always zero. And then we have y and x being directly proportional. So you have to use the Kelvin temperature scale. Here's the boiling water, ice water thing that would happen. Why does the balloon expand when it gets hotter? The gases are moving faster. Temperature is a measure of the kinetic energy of the particles. Kinetic energy depends on mass and velocity. The mass of the particles doesn't change, but their speed does. At higher temperatures, particles are moving faster. Talk about people on the beach. The real beach is nice, but in Reedley we have Reedley Beach, which sounds real fancy, but it's just this big sandy area next to the Kings River. But if you go there this time of year, and you get out of your car in the parking lot and you're going to walk barefoot to the river, are you going to stroll along through the sand? No, that sand is really hot. We say you hot-foot it, right? You run really fast because it's really hot. Hot gas particles move fast. If you're in Pismo, where the sand is cool, we go to Pismo in the summer, right? Because it's overcast and cold. And you can sit on the beach and shiver. And we like that, right? When it's 105 here, that's refreshing. We don't want to see the sun. We see the sun far too much here. When the sand is cold, people just stroll along barefoot. Cold gas particles move slowly, okay? So the gas expands because the particles are moving faster. Gases are great because they're just so easy to explain. So you get that higher temperature, you get more collisions. The collisions are more frequent. That increases the pressure. And they are more forceful. And so that also increases the pressure. And the only way for the pressure to remain constant would be for the surface area over which they're hitting to expand. The surface area would be the inside of that balloon. If the surface area increases, the volume increases. And then you can keep the pressure the same. So hot air balloons, they have this big burner here, which heats up the air and causes it to expand. The gas that expands has a lower density and the balloon goes up. So let's do an example with Charles' law. A sample of sulfur hexafluoride occupies 9.10 liters at 198 degrees Celsius. Assuming that the temperature remains constant, what temperature in degrees Celsius is needed to reduce the volume to 2.50 liters? So again, the best approach to this is a table. We've got 1 and 2. Our first number, 9.10 liters. That's a volume. 198 degrees Celsius. What's wrong with that temperature? It needs to be in Kelvin. So let's fix it right now before we forget. So we're going to take 198 plus 273. This is equal to 471 Kelvin. This is the temperature. So 9 liters at 198. Assuming the pressure remains constant, what temperature is needed to reduce the volume to 2.5? So here's the volume at the second thing, 2.5 liters, and this is T2, and that's what we're solving for. Did the slide ever show Charles' law? Did it show that? Okay. Because this is Charles' law, V1 over T1 equals V2 over T2. And we need to solve for T2. Okay, T2 is in the denominator. Be careful. Fractions just mess with you. Now, some of you are really good with algebra and you can just rearrange this and come out right. What happens to a lot of students is they end up solving for 1 over T2, which means you did all kinds of things right and you did one little thing wrong and you end up with the wrong answer and 0 points on an exam. So if you even question your ability in algebra, you're not sure, but you think you're okay, but you're not sure, get rid of the fraction first. Cross multiply, get rid of the fraction, then rearrange the equation. It's safer. So cross multiplying means you take the V1 times T2 is equal to T1 times V2. Okay, look, there's TV in chemistry. And now we don't have what we're looking for in the denominator, so we're going to divide by V1 on both sides, and we're going to end up with T2 equals T1 V1, T1 V2 over V1. If I make a mistake, please call me on it. I would like to pretend that they are all intentional to see if you're paying attention, but that's not true. Okay, so now we take our numbers. We're going to use the Kelvin temperature, 471 Kelvin, and volume 2, and volume 1 goes on the bottom. We're reducing the volume. Is the temperature going down or going up? It's going down. So 471 times 2.5, 471, try again, times 2.5 divided by 9.1. 129. Well, what's the unit on that? Kelvin. 129 Kelvin. What does the problem ask us for? Celsius. Sometimes students wonder, why do they keep giving us temperatures in Celsius if we have to use Kelvin? I personally have never seen a thermometer marked in kelvins. Kelvins are pretty much only used in gas laws, and the conversion is pretty simple. We're just adding and subtracting 273. So they're almost always going to give you the temperatures in Celsius, and when they ask you for a temperature, they're going to want it in Celsius. So just get used to it, I guess, huh? So to take this to Celsius, we're going to subtract 273 minus 273. We're going to end up with minus 144. Did I do that right? That's pretty cold. Questions? think we'll stop there.